Thank you, Paul. Great to be here. I hope the people online can hear me. I have no way to confirm that. So I'll just carry on. It's a real pleasure to be here, and I thank you for that introduction, Paul. He was probably like, I don't know, 5 years old when I met him. So it's I honestly don't remember exactly when we met, but it's way back.
Yes, we were both in preschool.
Yeah, back a while ago. So today I was the PI of the Boulder Creek Critical Zone Observatory from its inception in 2007 until it finally ended in 2020. And I'm really hopeful that I've just written the last annual report just a month or so ago. After, no cost extensions, I'm spending the last $500 in the budget this month, I hope. And be done with that. But, that's a really long time to run an observatory and to run a project. And so what I'm going to try to do today is show you illustrate for you how we learned a lot about one particular landscape by virtue of being there for a long time and having a lot of different people involved in thinking about this landscape and how it formed. Hence the layered approach, because I'm going to layer on different understandings that we developed. And I'm going to focus on understanding not just the critical zone, but what I like to use the word architecture, the subsurface architecture of the critical zone. And I hopefully will explain that as we go along. Okay, and is often the case with this kind of thing, there's many people involved in the project. This is an image from one of our annual meetings, just to give you a sense of that there are a lot of people that participated as we were running the observatory. The talk I'm going to give today, I will highlight work of these individuals: Greg Tucker, Hari Rajaram, Bob Anderson, whom I'm related to by marriage, and Silgi Moon's work shows up as well in this. So a nod to their contributions. And I want to start with a thought from one of my heroes, who is Bob Sharp. Bob Sharp was a geomorphologist. He was at Caltech for many years, and late in his career, he wrote this lovely little paper called Landscape Evolution, a Review. And in that paper, he talks about how landscapes are really sensitive and perceptive, that they record information from past events, and makes the argument that it's to our collective advantage as a society to understand how these landscapes evolve. That we need to have that in order to understand things like what the risks are, what natural hazards are, what things like soil production rates are that are sustainable, and so on. So a little nod to Bob Sharp there. So the critical zone, we've been throwing the term around. It's been in use in parlance for a long time. It was first actually articulated, the term critical zone, by Gail Ashley it's in an abstract that she wrote when it was in preparation for writing the Basic Research Opportunities in Earth Sciences. The NRC report came out in 2001. Was that report that year? So it was around then, around 2000. And we adopted that term critical zone, which is the outer skin of the Earth's surface, when we were casting around for a way to describe research frontiers that we thought were present for Earth surface sciences. It's this place where we see interactions between forcings from climate, from humans, from tectonics. We would see responses in the hydrosphere, water, in soils, and in the atmosphere through atmospheric gases, and they're all modulated through this zone, this interface of the Earth's surface. And one definition is everything from the outer limit of the vegetation to the base of active groundwater. And that encompasses the region in which rock weathering occurs. And so often there's a focus on weathering in talking about critical zone science. And so critical zone architecture is this, what is the shape, what is the depth, what is the character of this surface interface? And we know just from our personal experiences that it's highly variable as you go around the world. So here's an image I took in somewhere in Yosemite, in Sierra Nevada, and I just love this highly squished, what is that, redwood, cedar tree, growing in a fracture in what is beautiful granite, rock, ringing rock. And then this is an image I got from Jean Riot from somewhere in India, of a weathered profile that they're literally digging through. And again, it's nice, so it's kind of comparable rock to what the kind of granite looked like. This is just the kind of range of differences that we see in this material. And of course, the critical zone, this surface is really important for all these reasons, for soils, for storing water and flexing water, and of course for being substrate for all kinds of organisms. This is where life is supported. So when I talk about architecture, I've published, this is my drawing, critical zone architecture cartoon, what it looks like. This is a much prettier cartoon from Todd Dawson recently. They both show more or less the same thing. So whether you like the really pretty drawing on the right or the more, prosaic image on the left, they both are arguing the same thing. That in a eroding landscape, we would expect to see coming from the bottom up, you'd see there'll be some fresh rock that would be below this critical zone. And then you get into some weathered rock, varying degrees of weathering in that material. It's got fractures and chemical alterations and so on. And eventually that rock will get detached from the particles around it and become part of a mobile layer. Mobile regolith is what I've labeled it. Soil is what they've labeled it over here in Todd Dawson's diagram. I often use those terms interchangeably. And in that, the particles can move around and move down slope. And you can track material moving, rock material particles moving up through this profile as erosion is taking place and down slope. Or you could track water moving down through the profile and sort of bringing about many of these transformations that we're interested in. Now, Todd draws in all kinds of other interesting things. He breaks out a saprolite layer and a weathered rock layer in the weathered rock, which differ in degree of alteration and strength. And they point out how different ways that the water is held and so on. All those things are part of the critical zone. Now, one of the things, it turns out it's surprising, really, that we know remarkably little about the depth of this layer of weathering depths and soils. In fact, in that Bob Sharp paper from 1982, is that when he published that? He highlights at the end of the paper that one of the things that we need is just to know what the depth of soil is, how it varies across landscapes. That's an important unknown for being able to move ahead. This is a really nice image from a paper from Brady Function. I'm sure that he's published this precise image yet, showing that it's not just about the soil, which in his drawing is invisible, it's so thin, but the saprolite, the weathered rock layers, how they vary in thickness across a landscape. It look like across a landscape. So understanding what that structure looks like is really hard to do. It's the unknown zone. It's something that's hard to image. It's hard to see, hard to access, even though it's right underneath it. And what's important here is the interfaces between the different layers, and here we've broken out saprolite and weathered rock, that those interfaces are dynamic They're spatially structured, they're evolving through time, and in fact, those interfaces are probably co-evolving through time. So I'm going to take you to a catchment that we did a lot of work in the Boulder Creek watershed called Gordon Gulch. Probably heard, perhaps heard of Gordon Gulch before. It's in the Colorado Front Range, and this photograph or pair of photographs I took from a prominent high point in the catchment. I'm looking towards the west, towards the Continental Divide, across the upper part of Gordon Gulch. So here's a little topographic map of the catchment. I'm standing on that little high point right there and looking west. So you can see into the upper basin, kind of towards the lower basin in Gordon Gulch itself. So I'm going to take you to this landscape and ask, what is the subsurface look like here? There is a road that crosses the catchment. It's right about here. But there are no road cuts. That road, we have done a little bit of drilling there, but not coring of the rock there. So we actually don't have a lot of subsurface, direct observation. So that's the first question, is what is the subsurface architecture? And then of course we want to get at how did this architecture develop? So first, let me take you to Gordon Gulch, and I'm going to zoom out for just a second because I love this cross section. You can do this in reverse. Zap a line across the country. This is on about the 40th parallel. And here's the topography, right? And there's the Front Range. Remarkable image. I mean, it really drives home how high the Western US is relative to the rest of the US. You really get the Colorado Plateau when you see this. It also illustrates how high the plains are, which is, the geophysics question for you. But the Front Range is the first sort of, fence across the air masses here. And Gordon Gulch is going to sit right on if you look at it in detail, you'll see there's a little bit of a knuckle there, a little shoulder, and it sits right on that shoulder. That's where we're going to go. So this is the red outline here. This is a satellite image of the Boulder Creek watershed, the headwaters of Boulder Creek. You can make out here, that's the glaciated peaks along the Continental Divide. City of Boulder is right down here. And we have the sort of what we think of as the mountainous terrain. We have the plains out here. Gordon Gulch is the yellow spot, small spot here. And that's one of the study sites we had in this catchment. And if I put a schematic cross section of the Boulder Creek watershed, we go from the peaks of the Continental Divide. There are crystalline rocks underneath the Front Range itself, and then we have Mesozoic sedimentary rocks from the Mid-Cretaceous Seaway out here under the plains. And you can see that this landscape has been formed by, well, there was the uplift of the laramide orogeny that brought the Proterozoic rocks upwards relative to the Mesozoic sedimentary rocks. And then there's been, since then, erosion that has shaped this landscape. That erosion has taken the form of glaciation in the headwaters, but there's also been down cutting out here on the plains as the Platte River has been incising down into the plains, and that has set off. We can see the evidence of its incision in terraces out here on the plains. You can also see a canyon that is cut in crystalline rocks, as this wave of incision has been migrating upstream. Gordon Gulch sits in between those erosional perturbations. It's kind of in this middle spot here. So it's not affected by the glaciers. It's a little bit outside where the glaciers are. It's also upstream of the canyon cutting event. And it's on what we call the Rocky Mountain surface, kind of a low rolling terrain that forms a lot of the terrain of the Front Range, it turns out. If you do a hypsometric curve of Boulder Creek watershed, so the red watershed outline here, this is elevation area plot, and you see there's very little that's at very high elevations. There's a big bulge of area, that kind of high, but well above the plains elevations. That's where Gordon Gulch sits. The yellow arrow is the altitude of Gordon Gulch. So there's a bulge of topography there. This plot also shows you what the precipitation is like. That's the blue precipitation scale across the top. And then I've also put on here a description of the snow cover from the snow cover from Stephanie Cobb's work. That we get persistent snow at high altitudes in the winter. We get intermittent snow down at low altitudes like Boulder. And then there's a region that's sort of in between. That's where Gordon Gulch sits. It has snowpack that persists on slopes that are facing north, and it loses its snow on the slopes that are facing south. So it's kind of an interesting, it's an important representative part of the Front Range, but it's also got this very interesting transitional snow behavior to it. And this sort of range scale architecture is common for the Laramide ranges across the West. You see a lot of this kind of structure. So here's a map of Gordon Gulch, again, a little more detail. You can see our LiDAR topography. You can see some of the instrumentation that we arrayed across Gordon Gulch, the outlet down here. There's really two basins that are connected here. And you can see that the vegetation is forested. So we're in what's called upper montane forest in this setting. The bedrock is predominantly Proterozoic, biotite gneiss, although you can find places with granite in it as well. But most of it is this kind of gnarly looking, nice bedrock in the landscape. So the first thing we did, one of the very first things we did was seismic refraction work. If you want to know what is the architecture of the subsurface. So this was a master's thesis by Kevin Beefus. And these are the seismic refraction velocity profiles. And these cross sections that go across the catchment in different locations are showing the velocity in the subsurface. Let me point out the scale bars here. This is a 10-meter vertical scale bar. The warm colors are very low velocities. And the dark blue color are the highest velocities that we measured. So we get out of this that on average, the warm color for the weathering depth is something like about 12 meters depth across the catchment from the seismic refraction work that Kevin Beefus did. We'll come back to this and see more, but that was our first image of what the subsurface looked like. We also dug a lot of soil pits and couldn't resolve the soil thickness from the seismic refraction work because it's pretty thin. So each one of these dots out here, colored dots, is a place where there was a soil pit that was dug just to the bottom of that mobile soil layer. And they're colored by the depth. There's a histogram of depths here. The mean depth of soil across the catchment is about 40 centimeters. So it's not very thick across this site. Here's an image. Looks really grainy here, but you can more or less make out a boundary between the gneiss underneath and the mobile material above. And it really doesn't matter which slope you're on, how deep the soil is. There's a few places where you can see right here that you get some red colors, which are deep. And those you think are probably Pleistocene, losing my vocabulary, solifluction lobe that's sort of frozen in place. In other words, they're thickened by that. There is a bit of a riparian deposit along the bottom of the catchment that gives you those greater depths at the bottom of the catchment. But for the most part, it's 40 centimeters. Pretty much anywhere you see it, except where there's tors, I should mention, which account for something like 120% of the surface area. when we look at the mineralogy in soil pits and into the places where we could dig into the saprolite underneath, the thing to take home from the mineralogy is that even in this mobile regolith, the white colored part of these are the mobile regolith layers, we have primary minerals present. We don't see a lot of highly weathered material in the soil. And in fact, this soil pit I particularly like because you almost get the sense that, oh, we're going through the layers in a gneiss, and we just happen to sample different bands in the gneiss. You can see in that primary mineralogy. And when you get up into the mobile regolith, that mineralogy gets mixed by the soil mixing processes. So not a whole lot of chemical alteration to this material. And we also, of course, did some cosmogenic radionuclide work on this. This is Melissa Foster's part of her PhD work. And from looking at the in situ beryllium-10, this is looking in the bedrock. She could calculate what the surface lowering rates, and she comes up with rates that are 2 to 3.5 centimeters per 1,000 years for lowering rates, and doesn't see a difference between samples collected on south-facing versus north-facing slopes. We also looked at meteoric beryllium-10 in the soil and comes up with residence times of that soil of 10 to 20,000 years. Yeah. Take from this, if you have a 10-meter thick, 12-meter thick weathered rock layer, and these kinds of surface lowering rates, that you have a few 100,000 years to develop that weathered profile that we're seeing in the size of protection work. So it gives you a sense of time scale. So that's the description. Now, what is how does this form? How does this get shaped? And I'm gonna walk you through. I'm gonna try to walk you through 3 different ideas that have been proposed here. The first one is one that involves interaction of stress, the regional tectonic stress with local topographic stress as a driver for weathering. Next will be thermally modulated phosphating, just what we know about. And finally, a chemical weathering analysis that's driven by precipitation. So 3 different, very different kinds of almost like orthogonal, but almost orthogonal approaches to understanding what would be controlling that kind of architecture. So we'll start with the interaction of topographic stress and regional stress. And this is the work that comes out of the work that was done by St. Clair and Sylvie Moon. Sylvie was the modeler involved in this project and was published in Science in 2015. And they looked at Gordon Gulch, but they also looked at a couple sites, and some of their interesting insights comes from the comparison of Gordon Gulch with these other sites, the Calhoun site in South Carolina and Pond Branch in Maryland. And these are just maps of those sites. Here's Gordon Gulch. You can see they ran seismic lines along the lines that you can see here to look at the subsurface architecture as we've done. And they also have this model of topographic and regional stress. Here's what that looks like. So this is their modeling work. This is Sylvie's work. So she comes up, calculates a proxy for shear fracturing, phi, which is based on the maximum compressive stress and the least compressive stress. And the image here is just showing a calculation of what that failure potential is as a function of depth in a flat terrain. And then she also calculates just the least compressive stress, which is a proxy for opening mode failures that would make things separate from each other. You can see what that pattern looks like in a flat terrain. But then she adds in topography. And she defines this sigma star as the ratio of the tectonic compressive stress, is the region under compression or extension, divided by the gravitational stress that's associated with the topography. And here's her calculations for an area with a low phi star and a region with a high phi star. So think of low phi star as a place that has very little compressive stress, regional tectonic stress, and high phi stars being a place that is under tectonic compression. And again, now we see we've got the topography involved, and these proxies for shear fracturing and for opening mode failures have this very interesting and different pattern compared to what you get with no topography. And in particular, really interested in this pattern that you get under high sigma star, where all of a sudden you see that the failure potential, whether it's from shear fracturing or opening mode fractures, is quite high underneath the ridges. And the regions underneath the valley bottoms are less prone to those fractures. Kinds of fracturing processes. Okay, so that's the model. They go and measure. They do the calculations for these different locations. This is Gordon Gulch, this is Calhoun, this is Pond Branch, and again, here's failure potential and the sigma, the least compressive stress, opening mode fracture. And you can see there's a real difference between Gordon Gulch and these eastern sites, Calhoun and Pond Branch. And then they compare that with what they measure their seismic velocities, P-wave velocities across these topographies. And in Gordon Gulch, this is very similar to what we had already measured, showing that the low velocity really shallowly hugs the topography. Whereas in Calhoun and Pond Branch, the low velocity extends quite deep underneath the ridges. And same thing in Pond Branch. So very different. What is to hear Silgi or St. Clair or Steve Holbrook's involved in this talk about it. They talk about the bow tie pattern that you get in these settings under regional compressive tectonic stress that is lacking in Gordon Gulch. So they argue this explains the weathering patterns in these settings, which is quite interesting, right? But it doesn't actually calculate weathering. It just says, well, the potential for what's driving fracturing is greater here. This is what that pattern is. So the interaction of regional stress and local topographic stress should control the pattern of fracturing and weathering. Here's their kind of cartoon of what kind of pattern of fracturing and weathering you'd expect in these different settings. And they argue that, well, our seismic refraction profiling shows that we see that. Check, it works. So that's cool. But we were interested in mechanisms. So while they feel like, okay, we can understand Gordon Gulch from this process, we got interested in the fact, we were already interested, we published before them, about the idea that we had from looking at our seismic refraction profiles and noticing that it seemed like north-facing slopes, these are all the north-facing slopes on the left side, that the depth of weathering is greater than on south-facing slopes. In an average sense, you can pick out spots, pick your spots, but in an average sense. And this was actually from having been out there and dug soil pits. This is also supported, in my view, by what I could see in the satellite, that we could reach the bottom of those soil pits. That we stopped digging just because we were tired of digging on the north facing slope, whereas on the south facing slope, we stopped digging because we literally couldn't dig any further, at whatever depth it was, a meter or something. And if you average Kevin Beavis's profiles, you do get a slightly deeper, 10% or 30% deeper weathering to whatever seismic velocity you want to choose on the north facing slope than south facing slope. So we're interested in that. And this is what led us to think about frost. Like thinking about cold and ice anyway, like thinking about frost cracking anyway. So frost cracking is known to be an important process. This is a beautiful little ice age moraine where the rocks are just completely blown apart by frost cracking, and this soil profile in Dorset is attributed to frost cracking processes as well. And why would we think that? Well, Gordon Gulch outlined here, this is mapping the total yearly average, not total, average insolation across different slopes. And what you see is that the north facing slopes are colored blue because it's a really low insolation on those, and the south facing slopes are colored red because they get just a lot more solar insolation. This is a calculation that was done by Katie Barnhart, who's a co-author on this AGU monograph. It's a factor of 3 to 5 difference in radiation on one slope versus the other, and you really see it in the snow. And this is a springtime photograph, but pretty typical in the winter, that the south facing slopes would be snow free and the north facing slopes would be snow covered in Gordon Gulch. So frost cracking. We didn't reinvent the wheel here. There's been work done on frost cracking. This is a really fun paper by Julian Merton and others, where they were doing experiments in rock, making frost cracking happen. These are the end results from a case with freezing propagating from the surface down and from the bottom up, and they get fractures in the middle. This is freezing propagating from the surface down, and they get fracturing at the top. You can break rock, it's well known that this can happen. But how does frost cracking work? The work that's been done on frost cracking shows that frost cracking is not just because water expands when it freezes. It's more important than that is the fact that water actually will migrate to an ice lens if the conditions are held appropriately at the right temperature. And this is because you can actually maintain unfrozen water at temperatures below the bulk freezing point of water, at temperatures that are below 0 degrees C, in small spaces. So cracks in rock, fine grained material. And you end up finding that the frost cracking in rock often occurs not at 0 degrees C, but actually at temperatures that are below 0 degrees C. And we've identified what's called the frost cracking window, -3 to -8 degrees C, at which the unfrozen water lenses are thick enough to still propagate water and grow these ice lenses. And those growth of ice lenses is actually promoted by holding temperatures in that appropriate frost cracking window, rather than crossing the 0 degree isotherm. It's about sitting at that sub-freezing temperature. So knowing that, and there's work that's been done to show that, we put together a model of frost cracking for this landscape. And these are some figures from the paper that we've published on this. It's relatively straightforward if to just do a simple thermal conduction model if you prescribe a temperature of the surface. So here's temperature profiles. Each line of the blue lines here is just a different temperature profile at a different time, where the temperature is, there's a mean annual temperature. I think that's 0 degrees. So the mean annual temperature would be right here at +3. And with the oscillations, the amplitude being 12 degrees C. And you can see the funnel of temperatures that are possible in the subsurface. We've highlighted in gray here where the temperatures are in that frost cracking window, and we can keep track of that with a model. And so we can model the pattern of where we would expect frost cracking to be occurring in the subsurface. And you can see this is a model that goes down to 10 meters depth, and that under these conditions, it would be occurring at 1 meter or 2 below the surface. And we can do some other bells and whistles, like saying, well, it has to do with whether where the great temperature gradient, how far water would have to travel, and so on. You end up with similar kinds of results. This is for a mean annual temperature of +3 is the top row of models. The lower would be for a mean annual temperature -3, and you can see that we get much greater depths in which frost cracking is likely to occur, depending on whether we do it just as the simple frost cracking window, or we add in these penalties and so on. The idea is that we can demonstrate that under the conditions that were likely present over that several 100,000 years that we have to create this weathering system, that we would expect frost cracking to be important. Remember, you know, the Quaternary ice ages ended like 15,000 years ago. Mean annual temperatures are would have been similar to this -3 temperature during much of the past few 100,000 years. We also put in our model frost creep of soil. This is some needle ice. In the image I took, I went out and just tipped the needle ice on its side so you can see it. You must be familiar with that needle ice around here. It's the stuff that makes it crunchy to walk in cold mornings like this morning. And what happens is that these ice needles grow normal to the surface. They carry particles out from the surface, and then the sun comes out and everything collapses back down, and you have a net down transport. That's called frost creep. And so we could model frost creep if we know something about the frost penetration depth and the hill slope angle and how many of these cycles occur. So we put that detail into this model. This is the result of a landscape evolution model. And I'm sorry, I'm just showing you, here's the final picture, but in this model, we ran a 1,000,000-year run with frost cracking in the rock, breaking the rock up. We had frost creep on hill slopes. We had colder temperatures on north-facing hill slopes and warmer temperatures on south-facing hill slopes. So greater propensity for frost cracking on the north-facing slope, lower propensity on the south-facing slope. And what we see is that the weathering depth in this bottom is a plot of weathering depth going sort of across this whole domain. The weathering depth is shallower. Depth to damage. The weathering depth is greater on the north-facing slope and shallower on the south-facing slope. So we get greater weathering depth from the north-facing slope as we expected. So deeper weathering, and we could watch it evolve over time. Again, it's a pretty idealized, but it still shows the idea that frost cracking is a plausible mechanism to explain the difference that we saw in weathering depth on the north-facing slopes versus the south-facing slopes. And really a bonus was that we put together a landscape evolution model that was entirely driven by climate, by temperature, which is kind of fun. So in my last few minutes, I want to walk through one more model, which is thinking about water. I mean, we really have ignored water, even in the frost cracking model. But the topographic stress results got us thinking about what's different between Gordon Gulch and Calhoun and Pond Branch. How can we explain that difference? Obviously, there's this really compelling story with the state of stress, but there's also a climatic difference. It's semi-arid in the west, and it's much warmer, much more humid in the east. So let's think about water. So just to take you into Gordon Gulch, we do have a couple wells in the upper part of the catchment here to serve as schematic. Well, it's a quantitative schematic that goes across these wells, crossing the basin. And I've put on the depths of weathered rock as inferred from the seismic contraction work that agree with what we can see in the borings. And you can see the blue triangles are showing you the limits of water table height in these wells, right? So the water table is sitting within the weathered rock layer here, except right in the riparian area. And if you look at the channel, it's a tiny channel. So here's Gordon Gulch, the stream during a spring torrent. It's not a big stream. And if you look at the annual precipitation and the annual discharge that we've measured in a couple different years here, you see that the ratio of those, the runoff ratio, ranged in those years between 12 and 24%. And runoff is just a tiny part of the water that falls as precipitation on this catchment. The rest of it goes into ET, and some of it undoubtedly goes into groundwater, deeper groundwater. And in fact, we know groundwater is important. We can see that from the stream chemistry. So we sample water in a couple locations in Gordon Gulch, the upper part of the catchment, and then in the lower part of the catchment. And as you go downstream, we can see that solutes that are derived from weathering the rock, as calcium or alkalinity, they increase in concentration as you go downstream. In fact, things that are just sort of passively moving through the catchment, atmospherically sourced, like chloride and potentially sulfate. Sulfate's a little harder for me to explain. Concentrations there are steady downstream. So the result, the interpretation is that we're seeing increasing groundwater contributions as we move downstream, and that's particularly identified by these increases in weathering sourced solutes. We've also done a mod flow model of groundwater flow in Gordon Gulch. This was Lauren Solberg's master's thesis. She worked with Shaminga and I. And here's her results of what the groundwater surface water exchange are. So along the channel, the colors tell you, blue colors tell you that there was water emerging to the stream from groundwater, and warm colors tell you the stream is losing to the groundwater. And what you can see is that overall it's a gaining stream, especially in the springtime. So here's a May snapshot, and it's almost all blue and pretty dark colors, meaning large flexes. But even in September, it's still blue, meaning it's still a gaining stream. She also, in the mod flow, did some flow path modeling and shows, if she looks at tracks particles flowing in the upper basin, that those she sees flow paths are going infiltrating down through the weathered rock layers, the warm colors here, and into the bedrock layers. She sees the same thing if she does this kind of flow tracking on hill slopes. The water infiltrates down into the bedrock layers, but along the channel, she sees flow paths that are exfiltrating into the channel, so discharging in the lower part of the catchment. So all those point to this important flow paths coming down through the mobile layer into the rock and then emerging back out as groundwater in the stream. So all that is background to the model that was put together with Hari Rajaram and I, trying to model hydrologic flow paths, steady state, chemical weathering, landscape evolution, all those together in a hill slope model. So we modeled the flow paths, we modeled rock weathering, which we treated. We just had one phase, which was plagioclase feldspar, was following that one. We also had to have soil production and soil transport, because this whole system is being driven by two drivers. One is recharge, precipitation, minus evapotranspiration, water we feeding through the system. And the other is we had to have steady channel incision. Something has to happen down here to drive the system. And so with that, this is what the hydrologic flow paths look like. And we ran two cases here. We ran a dry case, P minus ET is equal to 0.02 meters per year. This is meant to emulate a Gordon Gulch kind of catchment. And we ran a wet case where that P minus ET is 0.12 meters per year, meant to be more like East Coast. And you can see here the steady state result. You can see the water table, that's this blue line, is different. Everything else is the same, but the water table is different in the dry case versus the wet case. And then the coloring of these flow lines shows you the travel time. And you can see that the travel time longer travel times in the dry case and that deeper water table, and shorter travel times in the wet case. That's just the hydrology. Now we're going to fold in the chemical weathering and keep track of how much of that plagioclase is remaining. How far are we going towards completely weathering the plagioclase? And so we're mapping the reaction extent snapshots. And here I've got, we're going to start with the dry case, and 50,000, 250,000 million year run here. This color bar is showing you the reaction extent. So when it's red, the plagioclase is completely weathered. When it's blue, it's completely unweathered. Right, and so there's a very thin orange layer at the top that develops in this dry case, and it just stays there even as the system is evolving. The incision is taking place, the landscape and the water table are lowering over time, and the weathering front is essentially steady in that. But the wet case looks quite different, and that's shown here. You see at 50,000 years. It doesn't look too dissimilar to the dry case. Again, there's a completely weathered layer near the surface, but at 250,000 years, that weathering front, the alteration of the plagioclase is pretty much complete, down to and even below the water table. And at 1 million years, it's really gone all the way through the ridge. So the weathering front is quite deep. Now this looks, to our eye, very similar to that bow tie pattern with deep weathering underneath the ridges. And yet there's nothing in here about topographic stress. It's about how much water is moving through the system to drive it. And interestingly, the transition from this shallow surface parallel weathering system to one where you get deep weathering occurs when the ratio between the weathering front advance rate, so how fast is this transition from completely weathered to blue, how fast is that moving down relative to the erosion rate, the lowering rate of the whole system? And where those two are roughly equal is more or less the transition between one behavior versus the other. It's a little bit fuzzy, but that's a sort of rule of thumb here. And you can imagine that, you know, if you're down cutting faster than you can weather the rock, the weathering front's gonna stay attached to the surface. But if you're weathering faster than you're down cutting, then it's gonna take off underneath the ridges. And that to me, this was a bit of a, now I get it. Now I understand why I see so little weathering in this, even though it's a steady state landscape. It's had hundreds of thousands of years. It's relatively dry. I mean, it's one of those. And many times in my career, I get these, oh, duh, I should have known that before I started. Kind of findings. So just to drive the point home, these differences in climate-driven chemical weathering is just an alternative to explain these differences in weathering that are well shown with the seismic contraction work. And it's just to say, well, there's another, the topographic stress may be an important part of this, but another component is the water. Oops. Okay. So the critical zone architectures are really spatially variable. They evolve over time. And I've tried to show in this one landscape, focusing mostly on this one landscape, 3 different ideas to explain what controls that architecture. One having to do with the state of stress, one having to do with fast cracking, in which we focus on differences across aspects, and one having to do with climate differences. The role of water and climate in driving these. You know, I don't think any one of them is all wrong or any one of them is all right. Obviously, you kind of need all of these pieces. And I would argue that one of the strengths of the Critical Zone Observatory was the fact that we had the time and the people to come out and build that kind of understanding by layering one kind of approach on the other. So that's my story, and I'm sticking with it. If any of you have young children, or if you are involved in working with young children, I do have this new book out on the living landscape, which is aimed at 8 to 12-year-olds, and it is a product of the Golden Critical Zone Observatory as well, with some help from Holly Barnard's Critical Zone Network cluster. But Eric Parrish, an artist, and I worked on this for the last 5 or 6 years. And it's finally out. And I have a copy if you want to, there's a copy if you want to look at it. Available at fine booksellers everywhere. And we're working on how to get it into classrooms, and it's going to be used by Center for Discovery, which is a CU outreach program, and their kids classes. This might be something for future. Thank you.